Hello again, this is Mrs. Thompson, and today we're going to discuss potential energy diagrams. We're going to take a look at a diagram, and we're going to take apart the features of that diagram, and you're going to need to know what those different parts of the diagram mean. Alright, first, I want to let you know that sometimes it will be labeled as a reaction coordinate diagram. It just means the same thing. We're still looking at the potential energy and how that changes over time. Or just think about it as energy and how it changes over time. So it says here, potential energy diagrams show changes in heat energy of substances over the course of a reaction. So what happens during this reaction is you get reactants that turn into an activated complex when activation energy is introduced, and then they move on and form products. And so you see this picture here with hydrogen and oxygen. They are the reacting particles. Then they turn into the activated complex once a collision has happened. And remember that for the collision to be effective, we need collisions that hit in just the right orientation with just enough energy and actually hit. And then they move off to form their products. All right. So here we go. Let's break these apart. Reactants are the substances that are present in the very beginning of the reaction. Products, present at the end. Makes sense? That's the things that are made, the products that's being produced. And then C, the activated complex, that's the high energy, what we call an intermediate, because it doesn't stay that way. It's kind of a transition period for that substance until it forms something new. The activated complex can also be called the transition state. Okay, and think of the activated complex as one big giant blob of all the molecules and atoms stuck together. And so in this picture, you see them separate, the transition states, when they're all bumping into each other, and then new products are formed. Some things to know about the activated complex is that it is very unstable. It doesn't last very long. And we do not usually see it in the equation. You usually only see reactants and you see products. You never really see the transition state. All right, here is your typical potential energy diagram. On the left, you see the amount of energy, usually in kilojoules, and then the progress is over here. This is just time. All right, so there are three basic parts. We talked about reactants, products, and activated complex. Well, when we first start out, right here on this line, this is the energy, like 200 kilojoules here, the amount of energy that the reactants have. We're just going to label that reactants. Okay, then what happens is energy is introduced. And so since energy is introduced, it can go up in energy, we add energy, and it can form something new, which is what we call the activated complex. All the atoms are smushed together, they've collided, and now we just need them to break apart and form new things. All right, so then they do that. They break apart, and as soon as they're broken apart, these new products have less energy than the activated complex does. So they release some energy when this is formed. All right, so here's your three basic parts: reactants, activated complex, products. All right, we're going to draw a line right here where the reactants are and where the activated complex is. And what this line can, or what this information can tell us, is how much energy do you need to add to the reactants in order for them to become activated complex. All right, so in order for them to change into that activated complex, we add activation energy. So that energy is called, this distance here is called activation energy. So label that. If you had to find that out mathematically, how much energy do you have to add to the reactants in order for them to become the activated complex? You would just take 450, which is the amount of the energy of the activated complex, and subtract 200, which is the amount of energy that the reactants have. Notice they don't start at zero. They already come with their own potential energy. All right, so there we go. Write that down. Activation energy is the reactants to the activated complex, and we can find that out numerically using the numbers on the side. All right, then we have another spot on the graph that we like to look up, and that is the distance between the reactants and the products, just numerically, and how much energy that they have. So we call that delta H because it's changing in heat energy. And so delta means change in energy between where the reactant started to where the products ended up. This can tell me a couple of things about the reaction. It can tell me if it's endothermic or exothermic. Remember that to find delta H, this is from thermochem, you would take the products and subtract out the reactant. So we would do this by looking at the energy value, it's 350, and subtracting 200 for this particular reaction. Okay, so you need to remember those terms, exothermic and endothermic. Exothermic just means it is releasing energy, and so there's a negative change in the amount of heat energy that is within it because it released it. So the potential energy will decrease in order to become products. And exothermic is exactly the opposite. It has to absorb energy in order to become products. So there's an increase in the amount of energy. That's why you see a positive delta H. Okay. Here I have two potential energy diagrams. One is endothermic and the other is exothermic. I'd like you to take a look at the location of the reactants and the products in each one of these and decide, is it endothermic or is it exothermic, and why do you believe that? Okay. So let me show you how to figure this out. It's pretty easy. You just take a look at where the reactants are and the products are, and you look at their energy. We're not concerned with this part of the graph, the activation energy at all. We're just looking at delta H, which is the difference between reactants and products. All right, so from reactants to products, it's going to have to go down in energy. It has to lose energy in order for the reactants to become products. That energy is given off, and so it would be a negative delta H because it's going down, and so that's just an exothermic reaction. Okay, for the one on the right, the reactants are here, products are there. It's going to have to go up in energy in order for reactants to turn into products. Remember that I am ignoring this activation energy hill. Okay, just like I ignored this one. I'm just looking at the difference between reactants and products. So from reactant to products, an increase in energy has to happen. And an increase in energy is endothermic. All right, so we're just going to go over some example questions now. And one thing that we have to discuss is sometimes we'll talk about a reaction diagram or a potential energy diagram as either being forward or reverse. So we can look at it in the forward direction, which is just from left to right, or we can say, well, what if we reverse this reaction? We made the products turn into reactants. That would be going from right to left. Okay, so this question says, is the forward reaction endothermic or exothermic? So let's just make a note, that is forward from left to right, the normal way you would read a graph. Okay, and then we're going to look, reactants are here, products are there, and so to get from reactants to products, ignoring that hill, it's going down. Going down is exothermic. It's releasing energy. It's losing energy to become products. All right, next question says, which letter represents the potential energy of the reactants in the forward direction? Okay, so this is just asking me what letter on this graph would just be for reactants. And since we're going in the forward direction, the reactants are here on the left. All right, number 3, which letter represents the potential energy of the products in the reverse direction? Okay, so here we have a graph. If we're going in the reverse direction, we're going that way, so from right to left, which means if we're going from right to left, the reactants are here and the products are over here. All right, so which one is the potential energy of the products? Well, that could be best represented by A. Okay, and notice you see arrows. We don't see numbers here because the arrows are just representing a distance. It's going from the bottom, which we can assume to be 0, to where the products are located. Okay, And that would be that entire distance. If we were to measure numbers, we could do that by looking at the distance of this line. All right, number 4, which letter represents the potential energy of the activated complex? Well, remember that the activated complex is right up there. And it doesn't matter if I'm going in the forward direction or the reverse direction. The activated complex is always on the top of the hill. So the letter that would represent from 0 to where the activated complex is would be C. Number 5, which letter represents the activation energy in the forward direction? Okay, so forward is going from left to right. Let's just label where are the reactants in the forward. They would be right there on this part of the line. Okay, that would be the energy for the reactants. Then we need, for activation energy, we need the activated complex. That's always at the top of the hill. So then I need to find an arrow with a letter that would just be from the reactants to the activated complex because that's the activation energy. So that would mean from here to here. So that's B. Okay. Number 6, draw a line to represent the heat of the reaction. Heat of the reaction is just delta H. It can tell us whether it's endothermic or exothermic. So let's see, where are the products in this forward reaction? So there are products. This number 6 should say forward reaction. If it doesn't on yours, please change that. All right, so reactants to products. We need a line, which would be from the energy the reactants are to the energy that the products are. Here's the arrow. I could draw that arrow anywhere on this graph between, as long as it lines up between this line and this line. 7. What's the difference between delta H in the forward and reverse directions? So we've already figured out delta H in the forward direction. Let's just see what would delta H be in the reverse. So in the reverse direction, this would become reactants and this would become products. Okay, so that would mean that I would need a line between here and here. The line I already drew fits that as well. It fits between the reactants here and the products there. So there really is not a difference between the amount of energy released or required for this reaction to happen. The only difference is the sign. So the two values are going to be equal, but the forward direction will be, for this particular reaction, exothermic, and the reverse reaction is going to be endothermic. Now that's not always true. So if we had a forward direction that was endo, then the reverse is going to be exo. So please make a note of that. It says, please note, if the forward direction is endo, then the reverse is exo. So they're just opposite in sign. They have the same value, just one's positive, the other's negative. All right, so here's some more examples, but these are ones that I would like you to do. So I will go over them after you do them. What is the activation energy for the reverse reaction? Okay. So reverse reaction, those are no longer products. These are reactants, and these are products. We want the activation energy, so we also need to know where's that activation or activated complex. It's at the top of the hill. For activation energy, it's from where the reactants start to the top of the hill, how much energy you have to get to make it into that complicated transition state. So that would be from here to here. And so if we actually find that energy, it would be 40 minus 10, it would be 30. So our answer here would be 30. Just figuring out the difference between those numerically. And then the next one, what is the activation energy for the forward reaction? Okay, so in the forward reaction, it's just like it is here, reactants and then products on the right. We need the activated complex, so it's from here to here. It's a much shorter distance. Okay, and so we're going to take that energy of the activated complex, subtract the reactants, and we get 10. So 40 minus 30 gives me 10. The activation energy for the forward reaction is less. Okay, so those two things are very different. All right, Next, we have catalysts. Catalysts can speed up the reaction by lowering the activation energy. So you see here a picture where you've got a hill, and the hill is shortened by the addition of a catalyst. So the dotted line represents a catalyst. Great. What doesn't change is the energy that the reactants have or the energy that the products have. Okay. The hill changes, but the reactants and the products do not change. All right, so it says, how do the features on the diagram change with the addition of the catalyst? So the reactants, no change. It's still in the same spot. For this one, it's still at 40. For the products, no change. For this reaction, that's at 120. What about delta H? Well, delta H is the difference between the products and the reactants, and if those don't change, then delta H isn't going to change. Okay, some more changes that could happen. What about the activation energy for the forward? So remember, the activation energy is at the top of the hill, and so for the forward reaction, it's from where the reactants are to where the activated complex is. So it's this distance right here. And then in the catalyzed reaction, reactants are here, the activated complex is here, and so you can see that this requires more energy without the catalyst than the catalyst does. So what does it do? It lowers or decreases the amount of activation energy needed. And remember, anytime you can decrease the amount of activation energy needed, you can speed up that reaction. All right. Next one is potential energy of the activated complex. So the activated complex is up there, right here at the top of the hill. The potential energy of that complex is the entire distance from 0 to the top of the hill. So without the catalyst, it's 180. With the catalyst, it's 140 kilojoules. And so it also lowers that potential energy for the activated complex. The last one is, what about the activation energy for the reverse reaction? All right, so for the reverse reaction, it is from here, these are now the reactants, to the top of the hill. Without the catalyst, it's this distance. With the catalyst, it's that distance. Okay, so it also decreases. Doesn't matter if you're going in the forward direction or the reverse direction, the activation energy is lowered. All right, that's finally it. Hope you found that useful. I will see you next time.